The failure of Rydberg and the Bohr model of the atom prompted scientists to continue exploring the nature of the electron and how it's positioned itself surrounding the nucleus. The next advancement came from Louis de Broglie, who found through experiments that the wavelength of light is equal to Planck's constant divided by the mass of the electron times its velocity. What de Broglie showed was that there is a mass dependence on the wavelength of an electron, even though the energy produced from moving photons around was massless. So the electron is described as having both properties of waves and particles, also known as the wave-particle duality. And it was a fundamental in our advancement in understanding how electrons worked and how they interacted with the nucleus as well as behave in an atom. De Broglie was awarded the Nobel Prize in 1929 for this contribution. About the same time, de Broglie's work led off a scientist by the name of Heisenberg to show that both the position and momentum of an electron is hard to isolate, known as Heisenberg's uncertainty principle. It basically says that the uncertainty in the position, that is delta x, is going to be greater than or equal to the uncertainty in its position times the uncertainty in its velocity and mass. Well, we know the mass, or the m there, that's a constant, mass of the electron. So we have the velocity in terms of meters per second and the position in terms of meters. It's always going to be greater than or equal to Planck's constant divided by 4 pi. What does this mean? This means that for an electron, you have a higher probability of the electron not being in the atom, that is where it's supposed to be, and it makes it almost impossible to know both where an electron is and how quickly it's going. The more we know about position, the less we know about its velocity. The more we know about its velocity, the less we know about where it is. So it makes tracking and following an electron impossible. The scale is too small, and the uncertainty in where it is too high. We can apply the uncertainty principle to things like you and me, satellites, bugs, anything you can think of. And what we find is that the uncertainty in our position, because we're so large, is incredibly small. We basically have no uncertainty where we are. We know exactly where we are. But the uncertainty principle gave rise to this idea that you don't really have an experimental chance of finding an electron to prove where it is or isn't. And so that required something else, a different approach. And this brought about the quantum revolution. The quantum revolution was pioneered by Erwin Schrödinger, and he developed a series of mathematical treatments to describe how an electron behaves based off both its wave-particle duality and the fact that there are certain quantas which it is allowed to have. Now you've got the equation over to the right, which talks about a Hamiltonian H and the wave function being equal to a couple of constants and a derivative, and that's all well beyond the scope of this course. It's a nasty equation, it's not fun to solve for, so we're not going to deal with it. What we are going to deal with is the results we get from this equation. And that's what we base quantum mechanics on. So, using Schrödinger's equation, we can begin to describe positions of electrons where they are likely to be. It's not a guarantee they're going to be there, but we have a high probability of finding where the electron is, or at least saying in this region of space the electron's most likely going to be there. It doesn't mean it will, but if you're placing a bet on it, odds are it's going to be most likely in that location. And so we have what's known as a series of quantum numbers, which describes both the position and the probability of it being there, and then it describes the shape or the trajectories in which the electrons can be found. how they're distributed spatially around the nucleus, and this is all described by a set of 3 quantum numbers. The first quantum number we're going to describe is known as the principal quantum number. These values are greater than or equal to 1, and they are always integers. These correspond to our floors in our apartment building we were talking about. You're either on the first floor or the second floor, those individual lines we saw. So n is a principal quantum number. It has positive values greater than or equal to 1. Next, we have the angular momentum quantum number, and this is known as L. And the angular momentum quantum number describes the shape in which the electron is found. So we'll see more about shapes and a tangible meaning in a little bit, but there are certain values that angular momentum quantum numbers have to follow. And these rules are that angular momentum values range from 0 to whatever floor you're on in your apartment building -1. So rather than try and track through multiple numbers, we actually give the angular momentum quantum number letters. So there are different letters corresponding to different values. So when L is 0, we describe that as being an s orbital. When we talk about L equal to 1, we have a p orbital. If it's 2, we have a d orbital, and 3, we have an f orbital. And again, you want to think about these angular momentum quantum numbers as just being different floor plans on a particular level of the apartment you're on. We have the magnetic quantum number. The magnetic quantum number basically says how many of each type of apartment there are. And the allowed values for the magnetic quantum number range from -L to +L. Also must be integer numbers. And what we find is that any set of orbitals will have an odd number of magnetic quantum numbers. So you have 1 s orbital. You'll have 3 p orbitals. There's 5 d orbitals and 7 f orbitals, and so on and so forth. So orbitals with the same value of n constitutes a shell. So n equals 1, there's a shell. We have the 1s shell. It's the only shell available when n is equal to 1. When n is equal to 2, we have 2 possible types of subshells. We could reside in our s orbital or our p orbital. When you're on the 3rd floor, you have the s orbital, the p orbital, and the d orbital. Those are all available locations for you to occupy. So these spaces will fill up with electrons. So depending upon where the electron is, will dictate how many different locations it could be. So what do these locations look like? Well, s orbitals are just spherical. That's all they are. You have a 1s orbital, a 2s orbital, a 3s orbital, first floor s, second floor s, third floor s. What we see is that these spheres get larger and larger the higher the principal quantum number becomes. These s orbitals have some very distinct places where their electrons are not allowed. And this is the result of a node in the wave function. That is, in waves, when you have your peaks and valleys, it goes through a spot where that position doesn't move at all. In terms of an electron, and as it applies to orbitals, this means that there are locations where an electron will never be. We don't know where it is, but we can say with 100% certainty that there is a location where the electron will not be. And these are known as our nodes. And so what we see is we increase the principal quantum number, the number of locations the electron cannot be increases as well. P orbitals are basically giant infinity signs oriented along either the x, y, or z axis. You'll notice that there are 2 lobes, and there is a spot smack dab in the center where the electron is not, and that spot is the nucleus. We have d orbitals, which kind of look like 2 p orbitals smashed together making an x. we have the dyz, the dxz, the dyz, etc., and then we have the dz squared, which looks like a p orbital with a hula hoop around it. And again, this orbital, or all these orbitals, are the result of the quantum numbers we've got. And so what we're seeing here, and how we know these shapes are indeed where the electron is surrounding the nucleus, all comes from the Schrödinger equation and actually plotting out the Schrödinger equation using these three principal quantum numbers. So it's a visual representation. Now, what happens when we start throwing electrons in these orbitals and these orbitals start filling up? Well, whether it's an s orbital, a d orbital, or a p orbital, when we have the maximum number of electrons in each orbital and we stack them all together, ultimately what we get is a sphere. So what this is doing is just dividing up three-dimensional space so that electrons can occupy certain spots within the sphere. Now, it's known from the Schrödinger equation that there are three principal quantum numbers that we deal with, but there's actually a fourth one that Schrödinger didn't predict. And it turns out that electrons are not all identical. They have the same mass, they have the same charge, but they also have something known as spin. And I don't want you to get the idea that when we talk about spin of an electron, that means it's either moving clockwise or counterclockwise. It's not like that at all. It's just a term we use to describe an electron and how it behaves when we push it through a magnetic field. The reasons that electrons may behave differently or have different spins is well beyond the scope of this course, but what you need to know is that there are two spins. Spins can have values of +1/2 and -1/2. So those are the components of quantum mechanics, and in the next video we'll see how we can apply quantum mechanics into filling up the orbitals of the atom.